Hi, I'm Andrew Wentzel, and I'm going to be talking about our work in visualizing and exploring spatial clusters based on our work with anatomical data from cancer patients that received radiation therapy. This work was done in collaboration with the MD Anderson Cancer Center and the University of Iowa. In cancer patients, the tumor location and disease spread are vital in deciding optimal treatment and forecasting patient endpoints. Radiation to tumors puts nearby organs at risk, and different patterns of disease spread play an important role in how the patient responds to therapy. One of the most important applications of machine learning to cancer research is the clustering of a patient cohort into groups associated with different risk factors. This application is known as patient stratification. However, clustering methods typically do not account for spatial data. In our case, head and neck cancer researchers are seeking a clustering method that accounts for the patient's spatial disease spread. Despite a widespread interest in spatial clustering techniques for patient stratification, their adoption in healthcare is stifled by the difficulty in understanding the inner workings of such methods. During a multi-year, multi-site project, we dealt with a large number of patients treated at the MD Anderson Cancer Center. We aimed to find patient clusters based on the important underlying anatomical structure of the disease spread. Despite a lack of computational methodology for this kind of spatial similarity, our spatial clustering method needed to consider many unique disease spread patterns and account for symmetry in the head. Furthermore, we experimented with different numbers of clusters and ways of determining cluster membership. Our methodology leveraged a period of participatory development to create a broader deployment as part of this multi-year project with evolving requirements. The paper describes several contributions related to, first, the collaborative visual design process during the development of a spatially informed clustering model. Second, to visualization design to help explain these clusters to clinical audiences during model deployment. And, last but not least, several design lessons for visualizing clusters with spatial data. Other work has been done in visual cluster analytics, but these methods don't consider spatial cluster data. Work has also been done in visualizing anatomical cohort data and developing clinical models, but don't discuss spatial clusters or designing for broader audiences. During the clustering model construction, we mapped the disease spread to the anatomical spatial data. We followed a graph theory-based approach and encoded symmetric cases on the same underlying graph. In these encodings, purple and green denote the disease spread on the left and right side of the body, and can be combined in the same compact graph representation shown last on the right. We arrived at this representation through multiple design iterations described in the paper. A variation of this graph visual encoding was used in an interactive interface to assess different spatial similarity measures, and then to explore different clusterings and cluster membership as part of a dendrogram. This graph-based encoding is a compact visual representation of the disease spread in patients. It accounts for symmetry and is aligned with the graph theory we used to calculate similarity. This representation also supports comparison and clustering. However, since it is abstract and complex, it was difficult to interpret by other clinicians who did not participate in our design process. It also gives more emphasis to the modeling approach and less emphasis to the toxicity outcomes and correlates. For the deployment model, we started with a simplified anatomical map of the disease spread in the head and neck. From this map, we created a cluster representation for each cluster, in which we heat mapped the percentage of cluster members with affected nodes in a particular region. Finally, we added a radial visual encoding to show clinical correlates and toxicity. Again, we arrived at this representation through multiple design iterations described in the paper. The advantage of our deployment model was that it was easier to distribute in print as a static figure. It was also based on anatomy, and so it was easier to interpret by broader audiences. It also shows correlates with clinical variables and toxicities. However, the added complexity of this design would make it costly to use during model development. Throughout the course of this project, we have identified 5 design lessons. First, use visual scaffolding based on the user's background. During model development, we found that a graph metaphor worked best, while during deployment, clinicians in the wider audience preferred a frontal, butterflied, anatomical map of the neck. that was used routinely in radiation oncology. Incorporating additional details for our clusters was essential to the user activity. For example, during agglomerative clustering, dendrograms with labeled leaf patterns helped identify how the clusters merged and split. Including secondary and potentially confounding variables helped mitigate situations where the clinical readers inferred direct causal relationships between clusters and outcomes. As our project progressed, we shifted from interactive visualization for a small audience towards static figures used in papers for a much broader audience. We wish our initial design anticipated broader audiences than our collaborators. Finally, we found that decision trees and other white box classifiers were useful for explaining the differences between clusters. This talk reflected on the process of designing visualizations for clustering with anatomical spatial data. These designs were developed in 2 phases over several years using participatory design alongside cancer clinicians and data mining scientists. In the future, we hope to incorporate additional insights from sibling projects and develop a more comprehensive set of design guidelines for spatial cluster analysis. Whereas here we focus on a specific project, our stratification approach and our design lessons can be generalized to any type of spatial cancer data. We would like to thank all members of the Electronic Visualization Laboratory, members of the MD Anderson Head and Neck Cancer Center, and our collaborators at the University of Iowa and our funding agencies. Thank you.